Yes, good afternoon, everybody. Dear delegates and other invitees. Now we are starting the session, parallel technical session, 30th practical session between 2 p.m. to 3:25. We have three lectures. One is state of practice lecture by distinguished Professor Satyendra Mittal, I.I.T. Roorkee, and special lecture by Professor Prishati Chaudhary from IIT Kanpur, and another special lecture by Professor Piju Samoy from NIT Patna. And in this session, we have distinguished chair and the co-chair. The session will be chaired by Professor Shivapriya Mukherjee, and the co-chair is Dr. Saha Dubhaji from Bata Atomic Research Center. Sir, on behalf of the organizing committee, I welcome all of you to this technical parallel session 30th. So it is my privilege and honor to introduce our chair on this occasion for the August delegates. I will share my screen. Yes. So it is my pleasure to introduce Shivapriya Mukherjee, who is chairing the technical session. Dr. Mukherjee is a professor in civil engineering at Jadavpur University. He obtained Bachelor of Engineering, Civil Engineering and Master of Civil Engineering degrees in 1978 and 1981 respectively from Jadavpur University, and PhD from IIT Kharagpur later in 1997. He went to National University of Singapore in 2005 as a visiting professor. Professor Mukherjee has supervised 15 PhD theses and more than 55 master's degrees theses. He has published more than 150 papers in international and national journals and conferences. Professor Mukherjee has efficiently managed various administrative roles, including serving as Dean of Faculty of Engineering at Jadavpur University. He also served as Chairman IGS Kolkata chapter. With this brief introduction to our audience, I wholeheartedly welcome Dr. Priya Mukherjee to conduct the session. Sir, welcome, sir. It is my pleasure to introduce our co-chair of the technical session 30th, Dr. Shah Sabuji, graduated from Jadavpur University, Kolkata in 1988 and joined one-year orientation course in nuclear engineering at BARC Training School in 1999. On completion of the course, he joined Baba Atomic Research Center, Mumbai in 2000. He completed his PhD from IIT Bombay in 2016 and is affiliated to Homi Bhabha National Institute, Mumbai. He has served Homi Bhabha Award. He received Homi Bhabha Award for securing first rank in civil discipline at BARC Training School in 1999. He has received Group Achievement Award from DIE in 2013. He has supervised 5 MTech students and is external examiner for MTech dissertations for University of Mumbai. His professional assignments include analysis and design of industrial and nuclear safety related structures, interpretation of soil investigation data, and interpretation of concrete NDT data. He is member of various task forces and safety review committees at BARC and Atomic Energy Regulatory Board, Mumbai. He is principal collaborator for an ongoing BRNS project with IIT Bombay. He also serves as reviewer for research projects submitted to BRNS. He has authored over 50 articles in various national and international journals, peer-reviewed conference proceedings, and book chapters also. So with this brief biodata, I welcome Dr. Saha Dubhaji to this session as a co-chair. Sir, on behalf of the organizing committee, I welcome you. Over to the chair.
Dr. Prishati Chaudhary is an associate professor at the Department of Civil Engineering, IIT Kanpur. Her primary research area is geotechnical earthquake engineering, soil dynamics, and seismic soil structure interaction. Her research group consists of a team of enthusiastic and motivated MTech and PhD students. 2 of her PhD students and 20 of her MTech students have been graduated under her supervision. She has published more than 50 articles in reputed journals and conference proceedings. She is involved in a number of sponsored research and consultancy projects funded by organizations such as Department of Science and Technology, Department of Atomic Energy, Eastern Railway of India, Archaeological Survey of India, Uttar Pradesh Rajya Vidyut Utpadon Nigam Limited, etc. She is the recipient of M. Vishwesvaraya Research Fellowship, Young Scientist Research Award from DAE, and Young Scientist Fast Track Grant from DST. So she is a very brilliant scholar and professor, what we see. So with this brief introduction, I request MS Dr. Rai Chaudhuri to kindly start her lecture.
Thank you, Professor Mukherjee, for this kind introduction and generous too. So let me share my screen. So a very good afternoon to respected chair and co-chair, Professor Mukherjee and Dr. Dauji Shah. Good afternoon to Professor Mittal, Professor Govindraju, Professor Shamui, all other delegates and audience and students, whoever watching this presentation. So before I start, I would like to also thank the organizers of this conference, especially Professor Ravi Jakka, Secretary ISET, and the organizing secretary of this conference, for giving me the opportunity to share some of my recent research activities. So what I have chosen for this lecture today is a very recent work that is being carried out by one of my PhD students, Mr. Monu Lal Bernwal, and he is working on seismic response of rocking shallow foundations on a reinforced sand bed. So what is a rocking shallow foundation? So let's look at a very easy and like a fundamental approach to understand this concept. This is a demonstration taken from this Anastopoulos et al. Researchers and colleagues working in the NTU Athens. So what you see in one of these cases, the foundation is adequate foundation capable of taking the lateral loads. So when we have earthquake or any other lateral load of any kind coming to the structure, the foundation is intact. So there is no yielding taking place at the base. Whereas there is hinge formation at the structure, there might be cracks, there might be partial collapse or failure. On the other hand, in the figure in the right hand side, you can see there is a rocking shallow foundation. So what happens? This foundation is not that adequate. That means the moment capacity and everything is not good enough. So what happens when there is a lateral load coming to this system due to earthquake or any other events? Then we see the yielding at the base. Okay. There might be bearing failure, there might be excessive tilting, there might be settlement, sliding. So all other issues can be there. But surprisingly, the structure is intact. So we can expect in one case the foundation level deformation is minimal, whereas the yielding happens in the structure. In the other case, the yielding happens at the base, but the structure is having a minimal deformation. The deformations are within the elastic range. So this concept, this rocking shallow foundation concept, is not very new. Actually, in the late 90s, we have seen it in one of the building codes, Applied Technology Council, where this performance-based design concept has been introduced, and the effect of this rocking shallow foundation has also we have seen. So here you can see these two pictures. So in one of them we have a good foundation, strong foundation with minimal deformations at the foundation level, but the cracks we see in the shear wall. On the other hand, the second picture, here the foundation is not adequate, and as a result we see that we have deformations at the foundation level in yielding and all. We see there is large deformations even at the beam column joints, but the shear wall is intact. So there is some trade-off. So one case we are having some structural damage, in the other case we have having some foundation damage. Now which one to choose? So now we can see this problem in a different light, that this capacity mobilization at the soil foundation interface may have some positive impact as well as some negative impact. So by positive impact, we can look into these issues like reduced force demand to the structure. There might be reduced flexural deformation, interstory distortion, as well as reduction in the floor acceleration. And as we are having nonlinearity and yielding at the base, that will increase, of course, the hysteretic damping, and we will have some benefits due to that. On the other hand, this issue will lead us to some negative impact, which is, of course, large amount of displacement at the foundation level. This displacement may be vertical, that is the settlement. It might be sliding, lateral. It might be tilting, rocking. It might be uplift, gap formation. So all these things can happen. So in this light, our main challenge is to develop some methodology where we can quantify appropriately these benefits. By benefits, we mean this reduction of force demand and so on. Whereas we can ensure that the consequences, those consequences like foundation settlement, tilt and all, those are within the permissible limit. So in this light, the objective of this current research is to explore some methodologies so that we can enjoy the benefits of rocking shell foundation while keeping the consequences at a minimal level. So actually around the globe, different groups of researchers are working in this direction. But in this presentation, I'll just limit my discussion to the study that we are carrying out at IIT Kanpur, especially my research group. So as we know that we are dependent on the PhD students for any work. So currently this work is being done by my PhD student, Mr. Monulal Varnwal. You can see him with the experimental setup, the laminar box setup. But this work has actually started a couple of years back, few years back, when I joined IIT Kanpur and got a PhD students and all. So this work has been started, by Dr. Bibek. Bibek had graduated in 2017. So I have to, as a background, show some of the results from his study as well. He is now a faculty at BITS Pilani Dubai campus. And since this is experimental work, so it is heavily dependent on the financial support from various funding organizations. So I am really grateful to DST and BRNS for providing the support at various stages. And of course, IIT Kanpur, the host institute, for providing all the facilities and in-house support. So let's look at the details of this experiment. So this is the laminar box that we use for any seismic soil structure interaction experiments. The idea is that this lamina, we have 15 lamina in the system. They can actually slide over each other and they can move laterally. In this way, we can minimize the boundary effect. We know that in a dynamic loading, there is a huge boundary effect possible if the sides are rigid. Also, it minimizes the effect of the wave reflection, refraction. So all these effects are minimized and we can replicate more or less soil deposit, in situ deposit subjected to an earthquake motion. So this laminar box, along with the model, structure, foundation system and the instrumentations are placed on the shake table. We have a shake table at IIT Kanpur with 40 kilonewton capacity. And we have done all these experiments. So the details of how we have scaled down this model, we have come up with this, we have come up with the loads, all these details you can find. If you're interested, you can look into this paper and find out, International Journal of Geomechanics. And the details of this development of this box, along with the calibration test, some characterization test of Ganga sand of different relative densities and all, that you can find out in the other paper in the soils and foundations. So if you're interested, you can look into those. So after calibrating the box and development of the model structure, we have carried out several tests with different base conditions, different soil properties, different configuration of the structure, different loading conditions, different factor of safeties. And we have seen that in most of the cases, we observe the reduction in the peak floor acceleration, reduction in the moment, base moment, reduction in the shear force, and interstory drift demand. So we see that yes, there are some benefits of the rocking shallow foundation, but we cannot go away with the consequence. So we see there is a large amount of settlement, seismic settlement, and there is sliding and rocking also. So you can see these are the energy dissipation curves we see from the base shear sliding and moment rotation curves, and we see large amount of sliding, settlement, and rocking. So we have identified that yes, we see some benefits in the reducing the forces and reducing the acceleration, but at the same time we also have consequences. We cannot leave the consequences, or we cannot neglect, because the consequence like settlement and sliding, they are as much as about 10% of the initial dimension of the foundation. So it is something that we cannot really neglect. Now the next question is can we solve the problem? So to solve the problem of seismic settlement, we tried to explore certain options. So one of the option is, let us try to see that if we put geogrids, because we know geogrids and geosynthetics, they are good at reducing the settlement. People have done these works for static settlement. We have a lot of literature. But we could not find much work when the rocking shallow foundation concept comes. So we tried to do some study where we put the geogrid layers in different configurations, 1 layer, 2 layer, and so on. Before providing this, since we are doing a model scale test in a shake table, we could not use regular geogrid. So we had to first take out the threads and make it a small scale and hand open it and use it. So that's how we tried to take care of the scaling factor. So we had used 2 types of geogrids, this polyester and the bamboo geogrids, hand woven bamboo. So this is the experimental setup. This is the laminar box. We have used different types of sensors to record various responses. We had used accelerometers at floor levels. We had used accelerometers at the soil at different depths. We use LVDTs to measure the displacements at the soil as well as at the foundation level. So that the way we have placed the LVDTs so that we can measure the rocking, sliding, as well as the vertical settlements. So different deformations in all 3 modes. And also we use some strain gauges to measure the deformations at the geogrid level as well as at the structure level, at the hinges and all. So this is the test matrix. We had considered 6 types of base conditions. First is fixed, where the structure was clamped on the table. Then the unreinforced soil bed. The soil was used loose Ganga sand, poorly graded, with about 40% of relative density. Then we use single layered geogrid, double layered geogrid, single layered bamboo geogrid, and double layered bamboo geogrid. The excitations that we had used was harmonic excitation of 2 Hz and 5 Hz frequency, and one earthquake motion from Chamba and another from Uttarkashi event. In order to change the intensities, we scaled all these motions in such a way that the peak ground displacement at the table was 1 millimeter, 2 millimeter, and 5 millimeter. So 3 different intensity levels we have used for each motion. So this is the test matrix what we have done. Now we have looked at various responses in order to identify what is the effect of the reinforcement on the response. So these we considered the absolute displacement, then sliding subtracted relative drift, then column moment, floor acceleration, and all these parameters. I'm just showing a couple of the responses, not all. So here you see it is a sliding subtracted relative drift. So that's why for all of them it starts from 0, the base. And we see that there is a reduction because this, if we subtract the sliding, that gives a measure of the flexural deformation or the structural distortion, which is a measure of the like structural performance. So we see that compared to the fixed base, this response is less in almost all the cases. But considering the reinforcement, we don't see much difference or we cannot identify the pattern between different base like conditions, reinforcement conditions. The same thing for column moment. We see that from the fixed base there is a reduction, clear reduction, but not a pattern or anything. Same thing when we look at the hysteretic loops. The first few figures, it shows the force deformation in the lateral mode, the shear force versus sliding. And the second lot shows the rocking mode, that is the moment, base moment versus rotation. In all the cases, we see that there is not much change in the peak moment if we consider the envelope. The energy dissipation is also more or less similar pattern. And the the stiffness in the lateral mode and the sliding mode, the rocking mode, are also not that much changing. So we can infer that the putting the reinforcement in the single or double layer does not change much in the rocking or sliding mode. But what about the vertical mode? Now, when we look at the vertical mode and measure the settlement, there we see there is a significant difference. So the first one is the unreinforced one, then single layer geogrid, then single layer bamboo, double layer geogrid, and double layer bamboo geogrid. So we see we have normalized the settlement with respect to whatever we see from the unreinforced, and we see there is a clear reduction in the settlement in most of the cases. Okay, and the reduction is as much as, for some cases, it as much as 50% or even less. So it reduces to 20% or so. So vertical mode is getting affected by the inclusion of the geogrids, but not the other modes. So these are some of the pictures we have taken after the excitations are over, and it shows clearly how the settlement looks like. It shows how the punching at the geogrid happens. Sometimes the ends are surfaced above the soil. So these are some of the evidences. So what we summarize here is that in this study, we tried to explore the possibility of using geogrid to reduce the seismic settlement. Mostly we have tried for low-rise building at this point, and just a steel moment resisting frame building. We don't know how this effect will be in the shear wall or any other kind of building. That needs to be done, that extensive study needs to be done before making a generalized comment. So it is observed, for at least for this range of studies, that the added reinforcement did not alter the moment capacity of the system. However, the seismic settlement, the primary adverse consequence of a rocking shallow foundation, is reduced significantly, in some cases as much as 70 to 75%. So it is inferred that the reinforcement did not influence the lateral and rotational stiffness of the soil foundation system, but altered the vertical mode of deformation. This reduction was found to be larger for the double reinforced soil layer compared to the single reinforced soil layer. So we can, so this is just, the study has just been started, and we hope that we can do more work and understand these things in a more clear way, not even for dry soil, but how it affects for liquefiable soil and so on. But we think that bamboo and the polyester geogrids may give a good solution for reduction of the seismic settlement, while keeping the benefits or the good effects of the rocking shallow foundations intact. So that's all for today. Thank you everyone for your attention. Take care and stay safe.
For your nice lecture. I just yeah, can you please see any question and answer question there?
Where do I see? No, I don't see anything.
No question, eh?
No, not in my like system.
Okay, so then there is no question, I think.
Okay.
Now I have one thing to know from you.
Yeah, sure.
That is not my question. I want to know.
Yeah.
When we are using geotextile, in case of rocking, actually, tensile strength of the geotextile is probably not mobilized very much.
No, not yeah, exactly. You are right. For these cases, we have measured actually the tensile load coming to the geogrids, but they are all below the strength. So it is not mobilized. Yes.
And it is quite natural that when there is a moment, moment cannot take the effect of the tensile stress, or tensile cannot reduce that. But
exactly.
I want to know why sliding actually is not affecting the geotextile.
Scaling is not.
Here is lateral. You please tell.
Yeah, so we have done the scaling, but it's possible. It's possible. I mean, the way we have done the scaling, we could not do like all other systems. The scaling factor we use as 10. So prototype versus model is 10. But for a geogrid, we could not do that 10 because it's not doable. So we had to use a factor of 2. So because that manually we could not do. So it's possible that that scaling might have an effect. But actually, after we have done the scaling, we check the tensile capacity, and the tensile capacity of the scaled and unscaled were not that different. Only very 5% change.
Yeah, that will not be different actually.
No, that is not different. So,
here comes another question. Ask you whether that scaling is necessary, because you see, when I am taking soil grains, it is sand, whether it is clay, I am actually not just cutting it in further. So it's normal grain. So grain with geotextile without scaling, that is the composite body which is resisting the load or movement or whatever.
Right. So there is actually one rule of thumb, maybe you can say that we consider that if the length of the or the dimension of the soil grain is less than L by 12, like if the L is the size, then we can neglect that scale effect. If it is a boulder you are using, then of course there will be scale effect. But sand and clay grains, their size is less than L by 12, so we can neglect. But that aperture of the geogrid was 20 millimeters, so we scaled it down to 10 millimeter or 1 centimeter. That much we could do. So that's, so now it is L by 12. So we are fine with the like rule of thumb. You see my point?
So when you scale down, you do not use any Buckingham Pi theorem on non-dimensional.
Yeah, we have used for all others. So I just kept them here. So this is you can. Is it visible? No.
Not yet.
No.
Okay. But anyway, so yeah, we have used some similitude laws that are applicable for shake table test, where the acceleration scale is made 1 and stress and strain 1, all other change. So it is following the similitude of shake table we have used, yes. But for the grid, we could not actually. For all other, we have used n equal to 10 scaling, but it was for geogrid, it was only n equal to 2. That much we could do because it was not doable. So, but the aperture size was less than L by 12. So that rule of thumb was maintained.
Anyway.